Hello, and welcome to Lesson 8 of this Introduction to Probability of Wolfram U. The topic for this lesson is discrete random variables. Let's begin. Imagine a waiter at a restaurant responsible for distributing water to clients. Clients ask for any number of cubes from 0 to 10 randomly. Then the number of ice cubes asked is a random variable, meaning the probability of asking n ice cubes depends on the integer n. In the last lesson, we quickly brushed over code used to solve probability questions. We'll now cover these methods in depth by focusing on discrete random variables. You'll learn of discrete PDF, CDF, expectation, and plotting. As mentioned before, the probability density function entirely determines its random variable. In the discrete case, this function is most often called the probability mass function. Why mass? Well, it comes from the following visual analogy. Imagine many balls on a plank, like the following. Since these are balls, the total of the pressure of each ball is applied at a single point on the plank. Seen in this way, the pressure applied at every point of the plank corresponds to the discrete probability function. For example, consider a country where the proportion of couples having n children is 1 divided by n plus 1 powered 3 and zeta 3. Don't worry about the zeta function, it's just a constant factor dividing our function so that we have a sum of 1. So just write the function down and use the probability distribution to model this distribution. First the function, then the range. Notice the range. Couples have from 0 to many children, but this is always an integer number, so you need to jump of 1. Consider a group of n football players that you want to separate in two teams, A and B. To do that, for each player, you flip a coin. Heads for team A, tails for team B. Consider I players are on team A. In how many ways can you choose I out of n objects? Remember lesson 2? Yeah, that would be the binomial coefficient ni. Now, how many teams are possible? There are n coin flips with 2 choices each, so we get 2 power n. Then the PDF must choose n choose I divided by 2 power n. As a sanity check, let's verify if it's a valid PDF. You can visualize whether all probabilities are positive using discrete plot. Here I use manipulate to consider a range of n values interactively. Now, verify that the sum is 1 over the entire domain. And indeed, this is true. So just build the distribution. The discrete cumulative density function is a probability that x is less than or equal to I inclusively. This is the sum of all PDF probabilities from the beginning to I. So just reuse the sum function used, and the sum goes from 0 to I. For example, coming back to the football teams, if there's 20 players to choose from, what's the probability Team A has less members? That would mean that Team A has 9 members or less. There are many methods to get this probability. You could define your own CDF and compute it at 29. Second, you could use the CDF of 9 over the distribution at 20. And third, you could calculate the probability of x being less than 9 for the distribution. Having a function doesn't tell us much about the distribution. What's the number of children expected in the children example? Well, going back to the plank and weighted ball analogy, if we assume a weightless plank is equivalent to the center of gravity, this would correspond to the expectation of x, the mean or average of the distribution. The expectation is defined as the sum of a function of value times its probability. This course uses mean or average interchangeably to express the expectation when f of x is equal to x. If you want the numerical expectation, use n expectation. For example, if you want the mean of the children distribution, you could use the numerical sum of the value times its probability. Or you could also equivalently use the numerical expectation function on x, where x is the children distribution. This is all equivalent to the mean of the distribution. Okay, let's complicate things a bit to see if you understood. Let's say in the team example there's 100 players, and you want the expectation of the number of players power 2. So method 1, you could take the sum of I power 2 times the team probability, so 25-25, okay. Or the method 2, the expectation of I power 2 on the distribution 25-25, great. Okay, but what if you don't know how many players there will be? Okay, well, just replace 100 by a variable and you get the formula. Okay, expectation is great, but plotting is still great to visualize. How does one visualize discrete variables anyway? Most likely, you want to use discrete plot since you're only dealing with one variable at a time, at this point in the course anyway. If you want to bivariate visualization, use discrete plot 3D. If you're not dealing with a function but data, consider using list line plot. Let's dive deeper into the discrete plot function, plotting the probabilities of the team example. You can choose whatever number of players you want, I'll just put it in the manipulate. See how thin the columns are? You can tweak it by modifying the extent size option. See how the column heads are just lines? You can tweak that with the plot markers option. So to summarize, discrete random variables have discrete values. Discrete CDF and expectation imply the sum of the PDF in some way. Use discrete plot 3D, or list line plot to visualize. While discrete distributions use summations, continuous distributions use integrals, seen in the next lesson.